let's actually analyze the first solution. So here is their exact integral representation. Here is the contour. And first, of course, as before, we'll try to figure out if the solution is bounded at the origin. So let's consider u1 of 0. Then we see that, well, the contour is finite right now, and the only possible singularities are points minus I and I, but as we discussed before, those are square root singularities, so they don't cause any troubles. So right now, the integral just becomes rather trivial one, dt over square root of t squared plus 1. And this is an elementary integral. One can compute it with easy change, for example, like dt, or so t is equal to is, and so you get the integral from -1 to 1, or the integral like from 0 to 1, double integral from 0 to 1, over ds over square root of 1 minus s squared, which is a trivial arcsine, and arcsine at 1 is pi by 2, and 0 is 0, so the answer is ai pi. So the solution is fortunately normalizable, and this way we found our constant a1. a1 is equal to 1 over I pi. Right, so now let's analyze our asymptotics of our normalized integral, because the integral obviously can't be computed exactly. So here is the expression. And okay, e2 xt over square root of t squared plus 1 dt. Oh, by the way, I forgot to mention that when we are computing this integral, we actually extracted the fixed, implicitly, the regular branch of our integrand, because here we have a multivalued function. And we assumed that if t belongs to this, so left bank of our branch card, then this square root is a positive function, so it's an arithmetic root. Okay, so let's actually denote this multivalued function square root g of t as g of t, and g of t minus 0 is positive when t belongs to the segment from minus I to I. Okay, so this is the fixation of our regular branch. Right, so as you clearly see, there are no saddles in our, so this is Laplace type integrals, but the exponent has no saddles. It's a simple linear function. So what we expect, we actually encountered that kind of integrals before. What we expect that the most dominant contribution to this integral comes from their endpoints, from point minus I and I. And indeed, this is so. And the logic is as follows. So we are interested in the asymptotics when x is large and positive. So let's actually concentrate our attention here on the vicinity of this point negative I. So what is the steepest descent direction when we go from this point? So we have this exponential, x is positive, so the steepest descent direction is obviously negative t, so we should move in this direction. So, and the same is here, by the way. So in order to compute the asymptotics of this integral, we just deform the contour into the following curve, like that. So this is the steepest descent direction from when we descend from this endpoint along the relief of our exponent function. And this is actually the steepest ascent point, steepest ascent direction. So we just go to this maximum point as well. Okay, so let's make an estimate of the contribution to this integral from the vicinity of this point. So this is our regular branch. This is how we fix it. Okay, so what we should do, we should expand our integrand function in the vicinity of this point. So let's do this. So first we introduce a change of variables. T is equal to negative I plus rho times e to I pi. So rho is the modulus of this complex number which goes from this point, and pi is its argument, right? Because it goes in negative direction. Okay, now we plug in this decomposition into our g function here, right? And make an expansion. So t squared plus 1 is turned into, okay, it's going to be negative 2I rho times e to I pi. Okay. Right, so now we need to compute the actual value of this square root of this g function. So let's see. So we go in this direction. So when we move along this left bank of our branch cut, the value of this function is positive. Then when we go in this direction, so the difference is that the complex number t plus I is turned by pi by 2 in the counterclockwise direction. So the change of the argument is pi by 2. So this way, the square root of t squared plus 1 is equal to the modulus of this expression, which is the square root of 2 rho times the change of the argument. So the change of the argument is pi by 2, right? But there is a square root. So the change of the the total change of the argument is only half of pi by 2, so it's pi by 4. So this is the correct value of our multivalued functions when we go in along this steepest descent direction. Right, so now we plug in this decomposition into our integral. So, and here we go. u1 of x. We compute the contribution from the point t is equal to minus I is equal to the integral. So we may integrate from this point to infinity because only the small vicinity of this point does contribute to the integral. So the integral goes from overall from 0 to plus infinity. So dt is equal to 0 to e to I pi. So it's basically minus 0. Square root is computed here over square root of 2 rho times e to minus I pi by 4. Next, we have this exponential. So it is turned into e to x minus xi, sorry. And times e to minus x rho. So what do you clearly see here? E to minus x rho, 0 over 2 rho, the integral from 0 to plus infinity. It's a simple gamma function of 1/2. And the gamma function of 1/2, probably you remember, is the square root of pi. So here it is. It seems that we are done. So this integral, well, naturally you should, well, if you don't remember, you should make a change of the variable x rho is equal to, I don't know, whatever, v, and then there is additional square root of x will be in the denominator. So in the end, what you'll get is negative e to minus I pi by 4 minus ix divided by the square root of 2 and multiplied by square root of pi and divided by the square root of x. So this is it. Well, in fact, I dropped this 1 over I pi term, this integration, this constant, which defined our normalization of our function. Let's actually restore it here. So it's 1 over I pi. Right, so the question is, what would be the contribution from this I point? Well, as you clearly see from the structure of the integral, it is symmetric. So we expect that the answer should be, the total answer, the total asymptotic, should be the real valued function of x. So if we get that kind of contribution from this point, minus I, so the contribution from this point should be a complex conjugate. So you can check it yourself. So it's a good exercise. Just figure out what the contribution from this point would be. But I'll leave it for you as a home exercise. Right now, I'll just state the answer. So what we do, we just you just add this similar contribution, but with a complex conjugation, and of course, you will get a familiar sine function. So it's going to be the 2 sine of x plus pi by 4. So 2 and square root of 2 will turn into the square root of 2 in the denominator, divided by pi x. And here you will get sine of x plus pi by 4. Right, so now let's actually discuss a little bit what we went through. So first of all, we built a solution as an exact contour integral, and we managed to normalize it. So and the normalization is exact. So we did compute this the value of this function at x is equal to 0, and we fixed this normalization constant. And then, despite the fact that we were unable to compute this integral exactly, we still managed to find the correct asymptotic for large positive x. And these asymptotics correspond to the correct normalization of our initial condition, initial function. Right now, I think that's it for this lesson. So thank you.